Hi, I'm Ian.
And I'm Avi.
And this is Lab 4, Optimal Beam Collimation and Testing Radius of Curvature. A shear plate works by interfering the front reflection with the back reflection of a glass plate. Fringes will depend on the wavefront of the incident beam. There are two main types of shear plate interferometers, wedged and non-wedged. In the non-wedged plate, a planar wavefront will not form any fringes because there is zero OPD difference between the two paths. However, a spherical wavefront will act like two point source interference. The fringes will always be horizontal, and a converging or diverging beam will look the same. A wedge shear plate has a small wedge along the y direction. The wedge introduces varying path difference, so there will always be fringes. When a collimated beam hits a wedge shear plate, it will form horizontal fringes. A converging spherical wavefront, however, will have a negative slope, while a diverging wavefront will have a positive slope. Besides converging or diverging, the fringe pattern can tell us the radius of curvature of the incident beam. But first, we need to measure three things. The shear distance S is the distance between the edge of one beam and the overlapping beam region. It can be derived from Snell's law and trig, and only depends on the plate parameters like incidence angle I, index N, and thickness T, which for a wedge shear plate is a function of Y. The fringe angle alpha depends on the OPD difference in the x and y directions. Zooming in, the horizontal fringe spacing is determined by two-point interference mentioned earlier. The spacing of fringes in two-point interference is dependent on the separation of the point sources, which in our case is the shear distance, and the distance from the sources to the observation screen. The point sources will act like they come from the center of curvature of the beam, so that distance is the radius of curvature of the beam. The vertical fringe spacing is dependent on the wedge angle theta and the index of the shear plate. Because collimated light will not induce two-point interference, when light is collimated, you will only see vertical fringes. Putting this all together, you get the equation for alpha. Finally, we need to measure the fringe spacing d. The equation for d is straightforward. Combining these three measurements allows us to solve for the radius of curvature of the incoming beam. To use the shear plate to find beam radius, we will use a beam expander to utilize as much of the area of the interferometer as possible.
We designed a beam expander assembly to output a beam 2 inches in diameter to fill a 2-inch shear plate. This means we need a minimum magnification of 54.9. Using the 9mm objective and a 500mm collimating lens, we can achieve a magnification of 55.5. The 500mm collimating lens will be plano-convex. To minimize spherical aberration in our system, we know to orient the lens such that the plano side faces the incoming beam. This minimizes spherical aberration by reducing the refraction angle on each surface, guiding the ray more smoothly to the output. We found our optimal pinhole diameter to be 12.3 microns. We decided to use a 20 micron pinhole in our system for ease of alignment. As done in previous labs, we can check the collimation of the expanded beam using a shear plate interferometer. Our first test will be experimentally verifying the focal length of a low-power mirror. We rotated the shear plate 180 degrees so it passes the expanded beam. We placed a low-power concave mirror after the shear plate to focus light down toward the shear plate. From the shear plate viewing screen, we can roughly measure the shear distance and fringe spacing with calipers and the angular deviation of the fringes with a protractor. Doing this at two different mirror positions along the optical rail allows us to estimate the focal length of the mirror. Our measured values for shear distance, fringe spacing, and angular deviation let us estimate the radius of curvature of the outgoing wavefront. The average mirror focal length calculated from our measurements is 58.81 meters. Compared with the known mirror focal length of 100 meters, this gives us a 41% error. This large error is most likely due to uncertainty in measurement of S, D, and alpha, since we were relying on calipers, protractors, and human vision for accurate measurement. We decided to switch from the 2-inch shear plate to the large aperture shear plate because the shear distance was getting clipped at the edge of the pupil. However, when we switched to the large aperture shear plate, we noticed that the slope of our fringes changed from positive to negative with an unchanged experimental setup. This suggests that the wedge angle is on the opposite side of the plate. Therefore, while using this shear plate, we will assume positive slope indicates a converging beam, which is the output of both positive lenses and a concave mirror. We can validate the focal length of a low-power positive lens by placing it before the shear plate and making the same measurements on the shear plate viewing screen. We use the same measurement and calculation procedure to calculate the focal length of the low-power lens to be 58.23 meters. Compared to the known focal length of 50 meters, this gives us an error of 16.5%.
To find the radius of curvature of a curved mirror, we can use a shear plate and a test lens. The focal length of the lens does not matter, it just needs to focus the light. When a mirror is placed at the focal point of the lens, the light reflecting back through the lens will be collimated, and we recorded the position of the mirror. Then we moved the mirror farther down the rail until the horizontal fringes reappeared. Now the focal point of the lens is at the mirror's center of curvature. Light coming from the center of curvature of a spherical mirror will have a 0-degree incidence angle on the mirror and reflect back along the exact same path. The distance the mirror moved is the radius of curvature of the mirror. We found the distance to be 399 millimeters. Because the light is on axis, we can use the paraxial approximation that the focal length of the mirror is half the radius of curvature. Using this approximation, our focal length should be 199.5 millimeters. The listed focal length of the mirror was 200 millimeters. So this method of finding the radius of curvature is fairly accurate.
We can validate the focal length of a low. We can validate the focal length of a low power positive lens. Stop it!